This subsection is just a series of examples. And in fact, the first example in this subsection, example 4, is modeling an equation and sketching a sinusoidal graph to fit criteria, and it has to do with average monthly temperatures, in this case for a small town in Oregon. And you can tell just by looking at the table here, this is table 3, that if you label the months 1 through 12, and then think of those as your input values, looking at the output values, the temperatures, these are average monthly temperatures, that the temperature for January is lower than that for February, March is even higher, April's even higher. If you plotted these as output values, you'd see that graph going up, 58, 63, 68.5, 69, then it starts to come back down, 64.5, 55.5, and so on. Comes back down to 43.5. And then, since these are average monthly temperatures, they're looking at all the Januaries since they started keeping records. So 42.5 is the monthly average for January, right? It's always going to be 42.5. Some Januaries might be higher than that, some Januaries might be lower than that, but on average, the average January temperature across years of data is 42.5 degrees Fahrenheit. So when you start graphing this, you start with 1 for January, you go through 12. Month 13 is going to be January again. So your cycle starts over. You'd have 13, 42.5 as your data point. If you click on the show hide solution, or if you're using the hard copy version of this textbook, you could just read below the table 3, to see the solution. And they tell you all of this, that the amplitude is found using this formula, find the largest value, find the smallest value, take the difference of those two, and then cut that difference in half. That's your amplitude. The data covers a period of 12 months. So our period is 12 months, but the b value is going to be 2 pi divided by b equals 12. When you solve that, you get pi over 6. So now we know how long it takes to get from through one full cycle, right? It's only going to take pi over 6 radians. The d value is how much the graph has been shifted up or down. So there's a way to calculate that as well. But I think you can see that this is a sinusoidal graph really almost just by looking at the data. I would encourage you to read through that entire example so that you can see how they found their final answer, the function. Y equals 13.3 times the sine of pi over 6 times x minus 2 pi over 3, all plus 55.8. In example 5, it's not as obvious, at least in the problem as it's given. The first thing they do in the solution is to make a table of values. And I think once you do that, it's pretty clear that the data goes up and then comes back down again. They give you points to plot. To continue, you can find the amplitude simply by taking the highest value and the lowest value and subtracting them and cutting that in half. There's a little formula involved there. And you can find the b value for the function as well. Like we know the period, it's going to be 12 hours. But what is the b value for the function? Well, you have to use the period formula and solve for b in that case. There's how to find d, the vertical shift, and so on. So that this is how we build a function from data. Sometimes you have to go get the data first. In this case, they gave us the values in a paragraph, but we really kind of need a way to visualize that, or a way to organize it. So they created a table next. And from that, you can find some points to plot, but you can also figure out what the amplitude is, figure out what the d value is, the b value is. And if there's a c value, you can also find that from this information as well. Example 6 is a little bit more cryptic still. In this case, they don't give us a series of values that we can just put into a table, but they do give us enough information to figure out what our function should be. The height of the tide in a small beach town is measured along a seawall. So you can imagine, remember, not an artist, imagine there's a wall that's holding back the tide, and maybe the tide, let's put our city over here. This is a city. There's a car. There's a car. Okay, and the sea rushes up and hits the wall, right? That's a wave. Rushes up and hits the wall. And the highest it ever gets on this wall is, let's see, between 7 feet at low tide and 15 feet at high tide. So the highest the water ever gets up here is 15 feet. But the lowest it ever gets is 7 feet. And then they tell us that on one particular day, low tide occurred at 6 a.m. And what that means, at least that this is my way of thinking of it, is that the lowest value you're ever going to get here in any of these positions, the lowest value you're ever going to get here occurred on that day, on that 12-hour cycle. That occurred at 6 a.m. So there are a couple of different ways you could handle this. You could say, let's start at 6, or you could say, let's start at 0 and just know that that's 6 a.m. Either way is right, but I think I'm going to go with this just because 0 is a lot friendlier to plug in to a trigonometric function than 6 is. So, all right, so now they tell us high tide occurred at noon. So that means the highest value you're ever going to get along here is at 12 o'clock, right? 12 hours. The lowest occurred at 6 and the highest occurred at 12. That's 6 hours later. And approximately every 12 hours, this cycle repeats. So if we go from 0 to 6 a.m. to 6, which is 12, technically p.m., that's noon, that's only 6 hours. So I need to go another 6 hours, and that's going to put me at 12. Now they tell us that approximately every 12 hours the cycle continues, so the period is 0 to 12. Now, I know I said plugging in 6 might be tricky, but so I could go 6, 12, 18 here, 6 o'clock, 12 o'clock, 1800 hours, which would be 6 p.m. But I'm just going to leave it like this. You could say 6, 12, and 18, or 6, 12, and 6 p.m. But 0, 6, and 12 works just as well. So I'm going to leave that like that. They want us to find a model for the water levels. And because this is a course in trigonometry, we know that it's likely going to be a trigonometric model. So we're going to have something that looks like this. Y equals A times either sine or cosine times, of B times x minus c all plus d. And we know from the previous examples that there are a couple of different ways, or there are a couple of different sort of formulas that we can do to, or use to figure out what the A's, B's, C's, and D's in this case are. A is simply the amplitude of the graph. If we knew what the graph was, that's my midline. If we knew what the graph was, we could say, well, what's the highest value and the lowest value? And if I subtract those and divide by 2, I'll have the amplitude of the graph. So what are my highest and lowest values? They are not 0 and 12. Those are input values. When I point to the highest value of this graph, I'm looking at a y value, which is an output value. And those are 7 and 15. So my amplitude is going to be 15 minus 7 divided by 2, which is 8 divided by 2, which is 4. So my function is going to start with a 4. That's my amplitude. All right, so now that I have that, I might look for, I can look for any of the others, B, C, or D next, but I think let's look for B. I know the period because I'm told that the cycle repeats every 12 hours. And so 12, the period is 12, right? Depending on whether you write it this way, 0, 6, and 12 is your lowest and highest, lowest, highest, lowest values. We know that the period is 12. So since my formula for period is P equals 2 pi over B, and I'm looking for B, in this case I happen to know that period is 12, so I have period equals 2 pi over B. When I solve that, I get 12B equals 2 pi, and I divide both sides by 12. I get B equals pi over 6. So my amplitude was 4. That's what goes in that position. What goes in this position is pi over 6. And that's still going to be times x minus some value c plus some value d. I still don't know whether this is a sine or a cosine graph. I'll have to figure that out. But if you think about this logically, the lowest point we ever get to is 7, and the highest point we ever get to is 15. At no point do we ever get down to 0, and we certainly don't get down to below 0. So the midline of this graph is somewhere in between these two values, right? That means that the d value is going to be somewhere between 7 and 15. And just like we can find the amplitude by taking the difference of the high and the low and dividing by 2, to find the d value, we're going to take the sum and divide by 2. And that is 22 divided by 2, which is 11. Basically, for the d value, you're finding the place right in the middle of the 7 and the 15. That's the average, right? So d is 11. So we're going to have plus 11 here. All right, let's take a look at what a graph of this situation might look like. I have a few points here. They say that at time equals 0, which we decided we're just going to call it 0, that's at 6 a.m., that the height was at its lowest. Let me find that again. Low tide occurred at 6 a.m., and low tide is the smallest possible value here. So that's 7. The input is 0, the output is 7. High tide is 15 feet, so that's up here. This is the high tide mark, right? And that occurred at noon, so we're at 6 hours later, and we have 15 there. We have a height of 15. And the cycle repeats every 12 hours, tells us that from 0 to 12 hours, we're going to go from 7 up to 15 and back down to 7. So I do have 3 points here. It's just that it was really not obvious what they might be. So I'm going to go 3 points. I can't do my my 5 values here because I don't have a function yet, right? I'm going to kind of try to graph it and get a sense of whether it's a sine or a cosine, what any horizontal shift might be, and that kind of thing. Those are the 2 pieces of information that are still missing. So let's see what we can do to graph this. I'll start with some axes. I'm giving myself a lot of vertical space here. For one thing, I know that the lowest possible value is 7. So I'm going to need to go from 7 up to 15. That's going to be 15. And I think I'll go by 5. So 5, 10, 15. Input values are 0, 6, and 12. Here's my 0. Let's make this 6 and this 12. So this is my x value. This is my y value. Now, the example uses t as the input variable, and that makes sense because we're talking about over a period of time, t for time. That's not terribly uncommon, but x is perfectly acceptable as well. Now, if I plot these 3 points, I get 0, 7, something about there, 6, 15, and 12, 7, which is about there. Because I know this is sinusoidal, I also know it's going to be curved. Well, it's probably not my greatest work. In fact, I know you can't see that, but let me try this again. That's a little bit better. All right, so there's my curve. And I also know, and I could have done this first, actually, I think your textbook mentions it. At least it's in there. I'm going to put the midline in. The midline is the point between 7 and 15. And in fact, we found it, we call it D, right? So right here at about 11, I can put in a midline. Is that in the right place? I can maybe it could be just a little higher. I'm trying to gauge not only does the amplitude look the same above and below, but is the scale 10 to 15? Is this 1 unit above 10 on its way to 15? It's kind of hard to tell. So I think that's about where the midline is. And I would argue that the equation of that line is y equals 11. So we have an amplitude that is 15 minus 11, which is 4, or 11 minus 7, which is 4. So our amplitude is correct. We have a period of 12. And again, the two pieces of information are whether or not this is whether this is a sine or a cosine, and what any horizontal shift might be. But I would argue that if this is a sine, then this sine graph starts here, and so there's a horizontal shift involved. If this is a cosine, then it starts down here at the minimum, either at the maximum or the minimum. That's what cosines do. So I'm going to argue that this makes more sense just to make this a cosine graph. And then since there is the graph starts at its minimum, either its maximum or its minimum, that's what cosines do. Since it starts at its minimum, there is no horizontal shift. So I can actually just take that out. It's just going to be pi over 6x. So let me rewrite that. No, you know what? I think I'll leave it there. I'm going to write it as minus 0, just so we have a record of that for the moment. Now, one other thing I need to consider here is that this isn't a standard cosine graph, it's upside down. And that tells me that there's a minus out in front. In fact, let's see, I think what I'll do here is erase my equal sign. In fact, I'll erase my y equals. I'll put my minus out front. Minus. And there we go. Y equals negative 4 times the cosine pi over 6, all plus 11. Now, your textbook has a positive 4 cosine graph here, and that's because their cosine graph isn't upside down the way ours is. The reason ours is upside down is that we started at 6 a.m. being time equals 0. They started their time being 0 at midnight, which basically means they have another entry in here before this one. I'm going to call it minus 6 for now. And since the cycle repeats between 7 and 15 and 7 and 15, if I go backwards, 7, 15, 7, 15, I'm going to end up with a 15 here. And that is equivalent to, extend my midline and extend my axis back to negative 6. I'm going to have a 15, a value of 15 there. And that would have made the graph look something like this. And if we had started with this as t equals 0 and shifted everything back, right, starting with t equals 0, t equals 6, t equals 12, then we would have had this positive cosine graph. We could also have started here. We'd have to have figured out what that value is. Since it's halfway between the lowest and the highest point, it's probably halfway. So this is probably 3. Then we could have written this as a sine graph. If we had, we'd have ended up with y equals 4 times the sine of pi over 6. It's going to have the same period. It's going to have the same b value. It's going to have the same amplitude. It's going to have the same vertical shift, so plus 11. The only difference is that we have to move to the right 3 units. So if you had done it one way, you would have got this answer. If you did it the way we actually did it together here, we would have got this answer for cosine pi over 6x plus 11. That's another version, another correct answer. And the answer in your textbook for cosine pi over 6 of t plus 11 positive 4, that's also correct. So because these are sinusoidal functions, there are an infinite number of ways to write them correctly. That is something to keep in mind when you're working on a challenge set or even a basic skills test. There are multiple correct answers. Sometimes an automated system like the one that we use for check your understanding and things like that might ask you to start at a specific point in order to validate the answer, but certainly on a written assessment, it doesn't matter where you start, but I will encourage you not to start at some really wildly large or wildly small negative value, right? Large positive or large negative value. Start near 0 just because it kind of makes more sense. And it's common sort of standard to use 0 as a kind of an anchor in some way. So your book used 0 as an anchor in a very different way than we did when we did this problem. But I partly did this problem this way differently from the way your textbook does it, specifically to show you that there are multiple correct approaches. All right, with apologies, this is a very long video. There are other examples, but but again, this is really good fodder for classwork, so I'm going to leave it there. And I'm going to move on to the last video, the last subsection in this section, which is modeling harmonic motion functions. This is a long subsection. My hope is to explain the basics, and then again, we'll talk about it more in class.